So this is our last day that we're going to talk about from Wyngaard, and then we have the homework due, which is a few problems from the chapters 8 through 12 that we've been looking at in Wyngaard. That's due next week, so we'll discuss pieces from that and questions that people have on Friday. That will be our main activity for Friday. So the remainder of this week is a little bit lighter than last week was. So to give everybody time to think about the homework and to ask questions. Then next week we're planning to go into discussing different parameterizations and closures. Now that we have the basics of how the atmospheric boundary layer and the ocean boundary layer work, and we have all the tools in place from Valis to discuss both the 3D turbulence aspects, Kolmogorov, Smagorinsky, all those kinds of pieces, and then also the two-dimensional and quasi-geostrophic aspects. So we can discuss mesoscale and submesoscale, baroclinic motions, barotropic motions, and how those are impacted in the boundary layer schemes. So I will post a set. The plan will basically be that we'll take on about one paper a day for the remainder of the 9 or so class periods that we have, and you can take a look at the paper before. I'll put up a schedule with links to all the papers for the remainder shortly, and then we'll basically spend the day going through and discussing the concepts and how it relates to the pieces we've seen in class so far. Where possible, I'll try to highlight open questions that we still have in the parameterization schemes or disagreement among the parameterization schemes, so that part of the story will be there. Lots of you are thinking about parameterizations, thinking about impacts of different parameterizations in your final papers. So thanks for putting the proposals in. I've tried to give you feedback already. Hopefully this discussion over the next couple of weeks will spark some ideas. Are there any questions about that before we move on to finishing up on the stable boundary layer? Okay, great. Thanks everybody for coming. And so the last topic we were going to discuss from Wyngaard, we spent a lot of time talking about the surface layer and then the convective layer above it. And now we're going to talk about the stable boundary layer, which doesn't really exist in a different spatial location, but kind of exists in a different temporal location. So there's a very corny joke from Wyngaard, which is that the stable boundary layer is as different from the convective boundary layer as night is from day. And what he means by that is that a stable boundary layer is a typical nighttime condition, and the convective boundary layer is a typical daytime condition. That's because the critical distinction between them is whether the stratification is a result of heating from below or cooling from below. So during the daytime, the surface warms up, and so you get a convective boundary layer above the surface boundary layer because of that warm air and warm moist air that's rising from the surface. Whereas at nighttime, the radiative cooling of the surface and the lower atmosphere, so that's upward long wave radiation, takes over, cools off the surface, and so you tend to have a growing stabilizing effect starting from the surface and extending upward. So the question is how that affects the turbulence and the properties of the boundary layer. The same is true of the ocean in that there is penetrating solar radiation during the day, which tends to stimulate turbulence deeper in the boundary layer, and cooling at night at the surface because of the colder atmosphere and less radiation, which tends to stimulate convection. It's a different story though, because the shortwave radiation during the day decays exponentially fast in the ocean, which tends to make the warming near the surface much stronger than the warming deeper. And so the solar effect actually has a restratifying effect in addition to triggering potentially some convection. So it's a different story. We'll come back to the diurnal cycle in the ocean as we and how it's simulated when we get onto the submesoscale, because the submesoscale and the convective time scales of the diurnal heating and cooling of the ocean boundary layer is an important part of that story. But let's continue on the stable boundary layer of the atmosphere for a bit more. Okay, so here's the convective boundary layer. So this is, remember, the daytime conditions, and so there's the surface layer, which is dominated by the stresses at the surface, and with relatively little deviation in the temperature across that layer, with a uniform vertical transport of temperature, a uniform linear drop in the vertical transport, which means that the heating across the layer is relatively uniform because the heating goes like the divergence of that flux. So there's a uniform heating rather than stratifying or destratifying the layer. It tends to be the whole layer warming up. And for passive tracers, there's the top-down and bottom-up stuff that we talked about last time. It makes the passive tracers have a slightly different profile. But the reason why I wanted to remind us of what we ended on, the concept that we ended on last time, was why is it that the entrainment velocity is less than the convective velocity? Remember, the entrainment velocity are the vertical velocities, the RMS vertical velocities that lead to absorption of either the warmer temperatures from the inversion layer above down into the mixed layer. So across this temperature jump layer at the top of the convective boundary layer, or also momentum jumps that could act as a Reynolds stress being brought down. And the reasoning that we came to was that essentially the increasing stratification up here competes against the turbulence, whereas the heating from below is actually driving more turbulence throughout the convective boundary layer. So the interfacial layer tends to be stable. And long ago, we went through the scaling argument for how big the eddies up in that layer might be. And the scaling law comes out to be something like this, which basically says that the vertical velocity variance, which might be coming from the convective forcing below, when it hits that stratification, the higher the stratification goes in the interfacial layer up here, when that big jump in temperature leads to a big jump in stratification, which tends to make if n goes up, the length scales go down. So the penetrative depth of those, when n down here in the mixed layer is relatively close to 0, the length scale of the eddies is basically filling the entire convective boundary layer, so the vertical length scale goes like Zi, whereas in the interfacial layer, it's this much smaller length scale, which is categorized by the amount of stratification at that level. So you might think then that if you have a stable boundary layer where you have stratification throughout that's being forced from below, that you would start to isolate the surface from the stratification and features aloft. And that's exactly what happens. So remembering back to what the Monod-Nabokov length scale was about, not in the negative Monod-Nabokov scale limit, but the positive Monod-Nabokov scale, where the buoyancy production is fighting against the shear production. Remember, the Monod-Nabokov length scale was the length scale at which those two were relatively in balance, or where the flux Richardson number was taking on a finite fixed value. We talked about interpretations either way. You could think that implies something that, like the shear that persists, is generated by the surface stress over that Monod-Nabokov length scale, or the temperature gradient, might be the temperature the temperature scaling as force at the surface over that Mononabokov length scale. And so when you look at wind speeds or velocities within a stable boundary layer, and this is actually from a large eddy simulation, and I would not trust this large eddy simulation very much. This is from Peter Sullivan. I've talked with him about how hard it is to do this problem right. There's a lot of issues with the resolution in this condition, but this is sort of a reasonable first guess at what it would look like. So the boundary layer turbulence is suppressed so that it never really gets a vertical length scale larger than the MO scale. And what that means is that rather than a well-mixed boundary layer like this in temperature, or a or the resulting shear profile, you get a shear profile that's very strongly sheared, so that the geostrophic velocities above the boundary layer are weakly linked to the surface boundary conditions. And so the wind speed in the stratified boundary layer, this stable boundary layer, tends to be much more sheared, with a sometimes with a jet aloft that has an inversion before you go up, so there's sort of an overshoot, versus the typical convective boundary layer, which is pretty uniform comparatively across the convective boundary layer and then the surface layer below. Where the convection or stable stratification are relatively similar. So there's this surface layer, which as we saw, is when you think in the Mononabokov scaling, when Z over L, the absolute value of it, is very, very small, and so it really it behaves like a neutral boundary layer, whether or not there's convection or stabilization. There's just a stress-induced shear there. But once you get up above, the convective boundary layer and the stable boundary layer are very different. So from daytime to nighttime, you expect a real readjustment of the winds across the boundary layer, which is in response to whether it's cooling or heating from below. If you want to get to that scaling, where du dz scales like this and d theta dz scales like this, when we go back to the assumptions of the Mononabokov similarity theory, that essentially means that we want du dz to be independent of z. It's supposed to depend just on L. So this kz over u star on the left-hand side of the equation, that von Karman piece, and the shape function, that's the universal solution of the Mononabokov theory for that particular value of z over L. Both sides need to be proportional to z, so that du dz becomes independent of z. And that's exactly what this scaling predicts. So in the stable boundary layer, we expect the shape function to be proportional to z, so that this side and this side cancel out and du dz becomes independent of z. Same thing goes true for the temperature profile, where if you think about the expected surface boundary layer scaling, that goes like this, with the shape function for z over L larger than as z over L goes towards a positive number outside, we expect this to be proportional to z, so that it can cancel the z on this side and make d theta dz be independent of z, like we assume up here. So that's this piece. So this is the expectation of the shape profiles for a stable boundary layer, that they should just be simply linear in height. And the rationale for that is to make the shear and the temperature profile be independent of z and depend only on the Mononabokov scale. So that's pretty much the understanding of what from a theoretical side there is. The one last piece of our story, which we keep going between the mean equations and then back to the perturbation equations, is to think about the perturbation equations. And the perturbation equations actually get relatively simple in the case of stably stratified layers as well. The reason being that because the stably stratified turbulence is kind of trapped in the vertical propagation, the complicated terms, the advection, the triple product term, and the pressure work term both tend to be small. That's true in observations and it's true in LES. They're both suppressed by the fact that the turbulence doesn't travel very far once it is generated. Once you throw out those terms in the equations or make them small, then the balances that come out are relatively simple, and you start to see that you basically you have a Richardson number that hangs out right around the neutral level where there's an even balance between production and dissipation, if you want to think of it that way, or just neutral conditions. And then intermittently, if there's surface roughness or gravity waves generated from the surface, you might push the shear up or down a little bit based on the gravity waves, so you get kind of intermittent braking. That intermittently the Richardson number is going below a quarter, there's a little bit of braking, which then changes both the temperature stratification and the shear, and you go back towards the critical Richardson number again. So you're kind of bouncing back and forth over this stable layer with a very intermittent structure of the turbulence. Thinking of that in terms of the Mononabokov length scale, that means that you tend to see things like that the turbulence is really suppressed, so that there's a layer of thickness of something like half the Mononabokov layer width, which is sort of similar to what we just said here, where we wanted to see that the effects of the shear is limited by that. The effects of the strong turbulence is also limited by that Mononabokov length scale. And based on observations, this seems to be something around a factor of half of the layer remains persistently turbulent. The upper part is either intermittently turbulent or not at all turbulent. One other thing is this turbulence, it's still shear-driven turbulence, so now the buoyancy production is missing, so there's no longer tall columns. It's really shear turbulence, and the shear turbulence that we've been talking about from Kelvin-Helmholtz and that kind of thing tends to be relatively isotropic. So the length scales in the horizontal and the vertical are small because of the suppression of the vertical length scale by the stratification. If you think of how that affects the dissipation scale, basically L is going down, U cubed is also going down, but not going down quite as fast. So the dissipation of turbulence actually tends to go up. So the turbulence, as the nighttime onsets, tends to decrease its strength, it tends to decrease its length scale, it tends to increase its dissipation rate. All of those things are consistently going together as we transition into nighttime and that buoyancy profile flips. This is talking about how deep the boundary layer where the persistent turbulence is from the surface. You can also think about a local scale up higher in the air column above the surface, and a relatively straightforward balance between the stress-induced forcing and the turbulent suppression scale gives you something like this, where here we're expressing that tau is a positive number, but down here that the theta omega is a negative number. That is, that it's a buoyant destruction rather than a buoyant production. So overall, this is a positive length scale. That kind of a scaling, U star cubed over a kind of W star scaling where W star is negative, allows you to think about how tall those eddies are up away from the surface. You can follow through this vertical scale, introducing it as a new scale into the Mononabokov theory, and you start to have predictions like this, where you can predict that the again, that the vertical turbulent transport is decreasing with height, and you can figure out that it's decreasing like z. You can figure out that the stress is also decreasing with height as you approach this H, which is the top of the boundary layer. This factor is linear. This factor is to the 3/2 power, but it depends on the linear variation inside. So these are basically coming from this local scaling for what the vertical length scales are that are making up the turbulence, together with this near neutral assumption that the Richardson number is relatively constant right near 0.2, 0.2 between 0.2 and 0.3 for this stable boundary layer. These don't capture the intermittency from things like gravity waves that might be pushing the Richardson number below the stable limit intermittently. That's sort of a more complicated feature, which you need to know something about the surface roughness and the propagation of gravity waves away from it. So if we think about what's happening as we are changing this boundary layer profile as we go into night, the geostrophic velocity is aloft or staying relatively uniform or staying relatively unaffected by this change, but the connection between the surface and those layers is getting isolated by the stratification. So as we talked about way back when we were thinking about the basics of GFD, that rotation would tend to connect flows in the vertical through the Taylor-Proudman theory, but stratification would tend to isolate the vertical layers from each other. We're seeing that in a different context here, where the rotation effect is not so strong because this is really just a 3D turbulence, but the stratification is still isolating the different layers. If we think about that in terms of the stress profile, during the daytime, when we have a lot of vertical connectivity by those convective plumes rising from the surface, going up to the interfacial layer, coming back down, and maybe doing some entrainment at the top of the interfacial layer, they would tend to make a very high surface stress for that linkage to the geostrophic velocities aloft. And then as we go into the stabilizing boundary layer, that connection is getting severed. Those plumes are not penetrating all the way. The efficiency of the momentum transport is going down, and we see that we expect that the stress or the friction velocity at the surface drops as we go into the stabilized nighttime boundary layer. So this happens kind of across the late afternoon and into the evening as the solar forcing drops off. Thinking of it in a slightly different way, you can think about a height at which the stratification has sort of won, which is the sort of like a cooling wave that's propagating upward in time, while the effects of the cooling are limited below that layer. So if you put those two ideas together, you get a cooling wave that's propagating upward times of the velocity, propagation speed of the cooling times time, but the velocity is scaling with U star, and as we said, U star is decreasing, so it isn't a linear function. As that goes up, it starts to roll off as U star comes down, and the Reynolds stresses are basically proportional to the shear stresses with a constant of proportionality that's less than 1. So as U star is going down, the shear production is going down. The level at which the shear production is affected by the cooling, affected by the stable stratification, is the height at which these two terms might balance, where the shear production equals the buoyancy production, or sort of the effective shear production, the part that can drive turbulence. It's left over, so a less than 1 efficiency factor balances the buoyancy destruction. That balance is also decreasing as the U star cubed on this side is U star is going down in time. So thinking about the decreasing U star gives us the idea that there would be an increasing stratified kind of cold layer and a decreasing layer of turbulent effect, where below here we expect to still have turbulence. The surface layer is still behaving like a neutral layer, and then as we transition into the stratified layer above, that's decreasing in time. This part is the stable boundary layer, this part is the surface layer, and it has this kind of time evolution as it onsets. All right, before I go on, are there any questions about this set of concepts that are coming in the stable boundary layer? Yes, so what's going on above this layer? So I guess you have to think about how the decay of the turbulence up there is being affected by the removal of the buoyancy forcing from below. So you have, if we go back to the Reynolds stress terms, you might expect that the buoyancy production is now decreasing, because as we have usually been scaling this based on the surface source of buoyancy, now there's just a little bit of maybe absorption by the atmosphere in that above layer, but this one has basically gone away. You might not have a suppression by stratification yet, but you still have dissipation dropping off the turbulent kinetic energy that was stored in that layer as you went into it. So the dissipation scale hasn't yet reached where did it go? The dissipation scale hasn't reached the point where it's being enhanced necessarily by the significant decrease of the boundary layer depth, this one right here. The L hasn't gone down too much, the U star hasn't changed too much, but epsilon is still non-zero. And so you're still decreasing the turbulence up here because of that. And so you would imagine that would count kind of if we think about the budget for each of these budgets would start to be a dissipation versus rate of decay of the turbulent flow up above. So even though the stratification hasn't led to the elimination or competition between buoyancy destruction and shear production, the buoyancy production has been turned off. So the any remaining shear production is maybe still the same up there, but the rate of change term starts to come in to balance the dissipation term. Does that make sense? I guess one thing you don't expect to see, however, is you don't expect to see that the temperature profile would start changing yet. The temperature profile up in the residual layer is already, you're imagining a convective boundary layer with a relatively well-mixed temperature. So as this stable boundary layer is growing, this part is still relatively unstratified. And if anything, you'd expect the entrainment from above to be weakened as time goes on. So you aren't really going to entrain a whole lot of the inversion layer away. So you would expect the temperature, both in stratification and value, to stay relatively unchanged in the residual layer. Okay. Sometimes that's called the relic layer, or the historical layer, or the historical turbulence, or because the turbulence there has lost a significant source of energy. So even though it's turbulent, it's not in a production dissipation balance of turbulence. The turbulence is rapidly decaying. So even though if you looked at the production it would not be strong enough to produce the turbulence that's there, but the turbulence hasn't quite decayed away yet. Okay, so the last... Sure. Yes, I believe it should. I think that's the kind of thinking you want to bring to that comparison. If the time scale was much longer than 24 hours, you actually wouldn't see much decrease of turbulence in that layer. It would just sort of persist unchanged as the stable layer grew below. And if the time scale was very short, you would see that that layer would stop being turbulent much faster. It's somewhere in the middle. Another way to think of it is if you were in a production dissipation balance and you had a relatively similar amount of production by shear and production by buoyant production, essentially the balance that you'd have at the Monin-Abakov height when the Monin-Abakov length scale was negative, so those two would be relatively similar. Now you take away half of it, then your production has decreased by 50%, but your dissipation is still equal to the same amount. So it relates back to the time scale of production to the time scale of destruction. If those two were in balance, you're now decreasing at sort of 50% the rate of dissipation that you had before. So that DDT has to come in and give you a time scale that's sort of ballpark half of what the dissipation was before, or equal to the convective production divided by convective production or the shear production at the MO height. Does that make sense? Okay. So one distinction from that is, what if that turbulence died off really, really fast? So this is kind of getting down to a different set of length scales. So this is, as we'll see when we get to that scaling, it's going to depend on a few other parameters of the system, how the time scale comes to be. But this touches back on a concept of from our GFD thinking, so I wanted to touch on this piece of the story. Imagine that we have a turbulent boundary layer. So we have both the Coriolis force on the shear itself, the pressure gradients from the baroclinic or barotropic geostrophic flow above. So we have, and then we also have the divergence of the shear stresses coming up from the surface. If this was in balance, and we had a statistically steady boundary layer, du dt goes to 0, dv dt goes to 0. That's what we're imagining up in this relic layer. But what if we just suddenly turn off the turbulence all at once? So what if that time scale for decay was really, really fast? What would be the response to this set of equations if we now remove the 0 and remove the turbulent time scale right here? Any guesses? It is an ageostrophic velocity. It would be these time derivatives would come back into the picture. So the ageostrophic velocities would leap into the frame. So what is the balance that we've talked about that's a deviation from the geostrophic balance based on the time derivatives of the mean? Similar to Ekman, except the Ekman has a balance between these viscous or turbulent terms and the ageostrophic part. So that's sort of what the balance is, neglecting the time derivatives. We're now putting the time derivatives in place of the turbulent. So which one is the one that has time derivatives balancing agiostrophy? Not cyclones, or they are cyclonic. They are cyclonic motions, but they are not cyclones because they don't involve a pressure-driven vortex. There we go. G-Guy's got it. Inertial oscillations. If we neglect the Reynolds stress in this equation and assume that we have some initial agiostrophic perturbation, so the Reynolds stresses are keeping FV to be different from FVG and keeping FUG from being different from FU. We turn them off. Now we have an unbalanced agiostrophic velocity, and it will oscillate in time. And in fact, this is the classic inertial oscillation situation where we have the U component in the rate of change term is balancing the V component in the Coriolis term, and then the rate of change of the V component is balancing the agiostrophic U component, which then, so we go around and we have the potential for an oscillation that goes around with a time scale that goes like F. So these are the inertial oscillations. That's exactly what we get. And you can work out how, by thinking about the initial profile you would have had in balance, and then using that as the initial condition for the strength of the oscillation, you can figure out about how much about how much oscillation you get. That is how much the velocity, the magnitude of the changing oscillating velocities would be for a barotropic and a baroclinic layer. And using two examples of the barotropic layer, you don't have to use observations. You can figure this out. This comes from essentially the convective boundary layer scaling from beforehand. In the one particular baroclinic case that Wyngaard has, he shows that essentially you expect, if the boundary layer were barotropic beforehand, you end up with less agiostrophic effects relative to the surface shear, but you still get a pretty substantial amount of oscillation. So remember, U star squared would have been our turbulent kinetic energy scale. We would have thought that the UV correlations in the boundary layer would have been about the same size as U star squared. Look how big the inertial oscillation is. The inertial oscillation kinetic energy is supposed to be 25 times bigger. So when you remove this turbulent stress balance, you get a very large oscillating inertial response. And in the baroclinic case, where there are other forces that are making deviations in the velocity being pushed away from the geostrophic velocity in the stress balance, you get an even larger kind of response. So suffice it to say, right above the, even though the decay timescale of that relic turbulence may not be instantaneous, you do expect to have a pretty substantial inertial oscillation response in that layer as the turbulence decays, which is essentially revealing the agiostrophic balance that was held in place before by the convective turbulence, if that makes sense to everyone. In the ocean, you see very, very strong near inertial oscillations at the base of the mixed layer, which is partly to do with this and partly to do with the excitation of those near inertial motions by near inertial winds at the surface. A fair amount of the oceanography literature about how the boundary layer shallows and deepens is whether these inertial oscillations are strong enough to make a shear at the interfacial layer, at the distinction between the boundary layer and the non-turbulent interior. If this is big, it could actually drive shear instabilities right at that interface and maybe do some entrainment. So this the potential presence of these inertial oscillations as a response to removing the turbulent motion might kind of counterintuitively trigger some turbulent motion as the shear right in the interfacial layer goes back up. This, I would say, is a big topic of interest. I don't think this is a well understood process, all told. When you look at what the boundary layer looks like in an acoustic sounding, as the onset of, let's see, so we're going into this is the middle of the night, essentially. So this is 3 a.m., 4 a.m. in local time. You can see that there are all of these gravity waves. There's all of these interfacial layers that are separating and propagating. Presumably, some of these gravity waves are strong enough that they're triggering localized intermittent turbulence. This upper surface is kind of evolving up and down as it goes, as the winds are decreasing and increasing. There's a lot of interesting intermittency and turbulence in this kind of layer. We don't have a long enough time scale here really to see whether there are inertial oscillations in this signal, but I wouldn't be surprised if there were. Okay, so to sum up, the stabilizing boundary layer goes to this limit where the positive Monod-Nabokov depth becomes the depth scale for the shear and also the depth scale for the stratification. To make these whole, that tells you what the shape functions in the Monod-Nabokov have to end up being so that you get a z on both sides of the equation, canceling it out. So this is the basic Monod-Nabokov conclusions on the stable boundary layer. There are some limits. You can continue propagating along and use this modified dimensional boundary layer scaling to get limits on how tall the boundary layer should be as the MO scale is evolving, how tall the Ekman layer should be as the MO scale evolves. These pieces are kind of the closing part of, these are other descriptors of what you think the height should be as stress and stratification are changing as the nighttime cooling proceeds. And as we saw, there is a suppression of the turbulence, and so there becomes a different connection between the geostrophic velocity, that's what this G scales for, and the surface stresses. And you can, once you have gone into the steady balance that results from essentially these Monod-Nabokov scalings, you can work out what the drag coefficient is for the stable boundary layer. So here is the drag coefficient, which involves both the Monod-Nabokov length scale, the height of the boundary layer, which is predicted by this little formula, and the von Karman constant, and also the Flux-Richardson number, which you might want to keep that as the neutral Flux-Richardson number, or maybe even the maximum Flux-Richardson number if the turbulence is really strongly suppressed. There's an argument that they go through this argument. This is sort of a hypothetical scaling rather than an observed scaling law. This is a prediction out of the Monod-Nabokov similarity theory for the stable boundary layer is how I would see it, rather than something that is certainly true. If this turbulence was highly intermittent, so you intermittently were pushing this Flux-Richardson number much smaller, you can see that you'd inflate the you could radically change this side of the relationship and drive it much closer to zero by make this much larger, by changing the amount of turbulence in the boundary layer. Okay. So in this thinking that you might be stabilized, you might be neutralized, you might be totally neutral, gives you a different set of turbulent mixing scales. So if you are really in a neutral boundary layer, that is a neutral boundary layer where Q0 is equal to 0, and you've let the stratification balance itself out, so essentially the whole boundary layer is the surface layer, then the turbulent velocity tails times the turbulent length scale, that is the turbulent viscosity or the turbulent diffusivity, would scale of the Ekman layer depth times U star. This scaling is pretty straightforward out of just ignoring anything to do with buoyancy. This is the scaling. If you have a neutral boundary layer which actually has some stratification, that might be because you have previously entrained some capping layer down into your boundary layer, or you're actively cooling from below, but you still have no surface forcing at the moment, you just have some stratification, then this scaling actually is a little different, and you start to see a suppression of the boundary layer by the stratification. So if n goes to 0, this one goes to infinity, but you don't actually go to infinity, you just go to the Ekman layer depth. This is saying what happens if if kind of the interfacial layer takes over from the Ekman layer. And you can see that those two are a little bit different. And in the nocturnally stable case, where you might have still no stratification from the daytime earlier on, but now you actually have an active cooling from below, then is when the Mononabokov scale comes into balance. So you have these three different scalings for the diffusivity or mixing rate. Then you might want to transition between them depending on what the Ekman layer or the stratification or the MO length scale were determined to be. That's actually a really nice idea. So you can think about taking these three scalings and converting them to a diffusivity, or in fact an Ekman layer depth, which is a little bit circular because this one also depends on the Ekman layer depth. But in the truly neutral case, the scale for the HE, if it's a turbulent boundary layer, is actually U star over F, not this LT. So U star over F is the LT scaling. Then the Ekman layer gets shallower with their stratification if it's a neutral, conventional neutral, or in a nocturnal stabilizing case, the U star is getting shallower as the Mononabokov depth is retreating. You can put all these together into one formula like this and predict, which Zolotankevich put this together. This is kind of a uniform asymptotic theory, which allows you under different stratifications, different shears, different Fs, different Ls, you get something like this, which predicts your depth scale. And if you have the depth scale, you can then go back and plug into these formulas and predict the diffusivity that goes along with it from these scales above. And so this is kind of a useful pragmatic parameterization under these different regimes. This would work under all of the different regimes for a stable boundary layer scaling law. So, all right. Summing up overall about our boundary layers, we have a convective boundary layer, which is relatively uniform in the velocity going to a geostrophic velocity up above. There's a relationship between the geostrophic velocity above and the surface stress. In the direction of the wind, you quickly converge to the geostrophic velocity, even within the boundary layer, and then there is a veer, which is governed by the amount of surface stress up above the boundary layer. The vertical transport of momentum is relatively small. It's linear, so it doesn't have any isolated divergences within the boundary layer. And the same is true in the other direction. So you have these stress profiles that are relatively simple. By contrast, the nighttime layer, you have lots of shear in both velocity directions. And so you get a much more intricate mean profile, which might involve inertial oscillations because of the removal of the previously balanced stresses during the daytime boundary layer. the deviations from the geostrophic velocity during the daytime boundary layer are intimately dependent on the turbulent fluxes, which are energized by the convective forcing in the nighttime boundary layer. There are also important roles for the stresses, particularly in the surface layer, which always looks neutral, both daytime and nighttime. But even above, you can still have some Reynolds stresses that are as the turbulence is decaying, but in this case, you tend to expect, at least in the stable lower portion of the boundary layer, that the buoyancy destruction rather than buoyancy production, which is what you have during the daytime. So that concludes all that I wanted to say about boundary layers from the atmosphere before we switch over to some schemes and think about how these pieces get used practically. Are there any questions? Okay, if not, thanks everybody. We will be discussing a homework, both any remaining questions from the last homework and any questions on the final homework on Friday. Take a look and see whether you think what you think. I tried to pick problems that are a little bit more about the intuition, a little bit less about the mathematics. So that you can draw on both the pieces from the Thorpe book and the Wyngaard book. But, this is coming back to review this whole concept of Monod-Nabokov scaling and thinking about different limits during strong convection, during stable, during surface layers. That's really the key concepts that we wanted to get across. And some sense of the effects of baroclinicity, even though we're going to discuss a lot more where baroclinicity might come from when we think about the mesoscale and submesoscale ocean in the coming weeks. All right. Thanks very much, people. See you on Friday.